Hello, my name is Oliver Harlen and I'm a reader in the School of Mathematics at the University of Leeds. Today I'm going to introduce you to the cross or vector product between two vectors and also the triple product between three vectors. Now you should already be familiar with the dot or scalar product between two vectors. This is equal to the modulus of A times the modulus of B times the cosine of the angle in between them. Mathematicians call this type of product an inner product. If we write the vectors A and B in terms of their coordinates, then this is equal to A1 B1 plus A2 B2 plus A3 B3. And clearly I can extend this definition to a vector with 4 or more dimensions. However, there's a second type of product that we can define in 3 dimensions, called the vector product. As its name suggests, this is the result of a vector rather than a scalar. And we write this product with a cross instead of a dot to distinguish it from the dot product. And it's important to note that these two products are quite different. To motivate the definition of the cross product, let's consider the parallelogram whose sides are given by the vectors A and B. The quantity we might be interested in is the area of this parallelogram. And this is equal to the product of the length of one of the sides multiplied the perpendicular distance to the parallel side on the top. Hence the area of the parallelogram is equal to AB times the sine of the angle theta. However, as well as the area of this surface, we can also consider its orientation in the three-dimensional space. To define the direction, we can use the vector that's normal to the surface. That is, a vector that's perpendicular to all the other vectors in the plane of the surface. Now there are in fact 2 possible directions, and these correspond to the 2 sides of the surface, which are coloured orange and white in this case. So we define the positive side to be the side on which the vector normal points out, and we choose this direction to be AB. So now we need to decide which of the 2 sides of the surface is going to be A cross B. This choice is arbitrary. It's a bit like deciding which side of the road we drive on. It doesn't matter which side we choose, but we all have to choose to the same side or there'll be chaos. The choice that's been made is called the right-hand rule, so I'm afraid if you're left-handed you can feel hard done by. To decide the direction of the vector AB, you hold your right hand like this, with your first finger pointing along the direction of the vector A, the second finger pointing along the direction B, and then your thumb points in the direction of AB. Now if I reverse the order, so I make B go along my first finger, A my second finger, then you can see that the normal points in the opposite direction. In other words, it points downwards, and that means that B cross A is equal to minus A cross B. So to recap, the magnitude of the vector A cross B is equal to the modulus of A times the modulus of B times the sine of the angle between the vectors A and B, and it's directed perpendicular to A and B in a right-handed sense, so that we have a right angle here between both A and A cross B and B cross B. Now in normal arithmetic, when we multiply 2 numbers together, the order doesn't matter. X times y is equal to y times x. The fancy word for this property is to say that the product is commutative. So the vector product, so that A cross B is equal to minus B cross A, is described as being anti-commutative. And consequently, any vector crossed with itself gives you 0. Now when we do calculations with vectors, we normally use Cartesian coordinates. So let's consider what happens when we form cross products of the base vectors I, j and k. Since I and j are perpendicular and of unit length, I cross j must be a unit vector perpendicular to both I and j, which means it must be either k or minus k. So now again we have to introduce a convention. So we define a right-hand set of axes to be ones where I cross j is equal to k, and from the anti-commutative property, therefore, j cross I is equal to minus k. So now if I rotate my axes so that the j goes to where the I was, the k goes to where the j was, and the I goes to where the k was, you can see I now have that j cross k is equal to I, and rotating again, k cross I is equal to j. And then using the anti-commutative properties, k cross j is equal to minus I, and I cross k is equal to minus j. So now if I want to form the cross product between the vectors a and b, written out in coordinates, so that's a1i plus a2j plus a3k, crossed with b1i plus b2j plus b3k. So if I work this out term by term, I get a1 b1 I cross I plus a1 b2 I cross j plus a1 b3 I cross k plus a2 b1 j cross I plus a2 b2 j cross j plus a2 b3 j cross k plus a3 b1 k cross I plus a3 b2 k cross j plus a3 b3 k cross k. So if we look at these terms, I cross I is 0, I cross j is equal to k, I cross k is equal to minus j, j cross I is equal to minus k, j cross j is 0, j cross k is equal to I, k cross I is equal to j, and k cross j is equal to minus I, and k cross k is again equal to 0. We have that a cross b is equal to a2 b3 minus a3 b2 times I plus a3 b1 minus a1 b3 times j plus a1 b2 minus a2 b1 times k. However, this formula can be hard to remember. In particular, it's hard to remember which terms have the minus sign. So what I'm going to show you are two different construction methods for writing out the cross product. And you can decide which method you prefer. So the first method, we start by writing the vectors as columns. So I have a1, a2, a3, and then b1, b2, b3. I then repeat the first row, a1, b1. And now I'm going to draw diagonal lines down between a1, b2, a2, b3, and a1, b1. And notice that these correspond to all of the positive terms in this sum. If I now draw diagonals the other way, a2, b1, a3, b2, and a1, b3, then you see I get all the negative ones. What's more, if I write down the product at the end of the diagonal, I get the terms in the right place. So here I get a1, b2, which is in the k position. Here I get A2, B3, which is in the I row, and this one here, A3, B1, that's in the J row. Similarly with the upwards ones, I get minus A1, B3, minus A3, B2, and minus A2, B1. Now let's do an example to see how this method works in practice. So I'm going to take my vectors A and B to be A is going to be 2, 4, minus 3, and B is going to be minus 1, 0, 3. So according to my method, I now write 2, 4, minus 3, and then I repeat the 2 again. And with the B, I write minus 1, 0, 3, and then I repeat the minus 1 again. And once again, I'm going to draw my diagonal lines. So the first diagonal line here gives me the k coordinate, so that's 2 times 0, which is 0. 4 times 3 gives me a 12, and that's going to be in the I direction. And finally, minus 3 times minus 1 is going to go in the j direction. Now I go and do the upward diagonals. 4 times minus 1 is going to give me minus 4, but then I have to take off another minus sign, so that becomes plus 4. Minus 3 times 0 gives me 0. And finally, 2 times 3 gives me minus 6. So the answer is that A cross B is equal to 12 minus 3, 4. The second method uses the determinant of a 3 by 3 matrix. If you don't know how to calculate a 3 by 3 determinant, then I suggest you skip this part and use the first method, which I think is easier anyway. However, if you have learned how to do 3 by 3 determinants, then this is a good example of how to use them. We start by writing out a matrix where the first row are the vectors I, j, and k. The second row are the components of the first vector, A1, A2, and A3. And the third row are the components of the second vector. And now we expand this determinant out using the top row. So I get I multiplied by this minor, which is this 2 by 2 determinant of A2, B3 minus A3, B2. When I come to the j term, I have to remember that, of course, there's a minus sign here. So I get minus j times A1, A3, B1, B3. And finally, I get plus k times this minor, A1, B2, and A2, B1. So when I expand out these 2 by 2 determinants, I get the result I have up at the top, which is A2B3 minus A3B2 times I minus j times A1B3 minus A3B1 plus k times A1B2 minus A2B1. And notice that that's exactly the same as the formula up here. However, you have to remember to use a minus sign in front of the j, and that's the big mistake that people tend to make using this method. Okay, so let's use this method to do the example that we've just seen. So the first row is now going to be 2, 4, minus 3. And the second row is minus 1, 0, 3. So the minor associated with I is going to be the determinant 4, minus 3, 0, 3. Plus, and remember, again, we have to use a minus sign here, j times 2 minus 3 minus 1, 3, and plus k times the matrix 2, 4, minus 1, 0. And now working out these determinants, I get 4 times 3 is 12, minus 0 times I, minus, and now 2 times 3 is 6, minus 3, which gives me 6 minus 3 times j, plus, finally, 2 times 0 minus 4, so it's 0 plus 4k. So it's exactly the same answer as I got before. So we found that the vector A cross B is given by 12i minus 3j plus 4k. And therefore, if we want to work out the area of the parallelogram, we need to calculate the magnitude of this vector. So the magnitude of A cross B is going to be the square root of 12 squared plus 9 plus 3 squared plus 4 squared, which is equal to the square root of 169, which is equal to 13. So in this case, the parallelogram has an area of 13 units.